All right, good morning, everyone, and welcome to our first installment of Swagelok's Northwest Tech Talks. Today, we're going to be covering Regulator Basics. My name is Adam Ganoom. My background is with Swagelok Manufacturing in Cleveland, Ohio, but I'm a recent transplant to Swagelok Northwest team as part of the field engineering group. So that's a global network of over 100 engineers, and it really allows us to have a robust ability to collaborate and support projects around the world. Just one quick note, we do have the ability to live chat, so please feel free to enter any questions that you might have throughout, and we'll do our best to address those. And with that, I would like to introduce my colleague, Matt.
Thank you, Adam. As Adam said, my name is Matt Hasenor. I'm also a field engineer here at Swagelok Northwest. I have been a field engineer for 3 years. Before that, I was in our valve service group with Swagelok in Ohio, and then moved out and joined our custom solutions team here at Swagelok Northwest. For those of you that don't know, Swagelok Northwest covers Oregon, Washington, Northern Idaho, and Alaska. So again, I want to thank everyone for joining us today. When I think about why we're going to start this first series on regulators, I think to a comment that our product manager made in regards to regulators, and he said that 95% of the returns that we get for regulators are either regulators at the very beginning of their life or at the end of their life. So I really want to focus on those regulators at the beginning of their life and trying to make sure that we design and install the correct regulator for the application. It's usually not the regulator that's the problem. It's the regulator in that application that's the problem. I'm assuming that most of you can think of regulators that have not worked or that have failed, and you've had issues with those. So we want to help take some of the experience and the things that we've learned and pass that on to you guys. And so really want to thank everyone for hopping on. So quick run through of what I'll cover today. We'll go into a little bit of just background on regulator theory. What is a regulator? And then I want to cover some performance criteria around pressure regulators, those being lockup, choked flow, droop, and the supply pressure effect, which those you may have heard of those before. And then how do we address each of these performance criteria? What can we do differently starting today with our systems to help eliminate or address some of these performance criteria with a regulator? As Adam mentioned, we will have time throughout the presentation as well at the end to answer some of your questions. So feel free to keep those streaming in throughout the presentation, and we'll try to get to those questions either throughout the presentation or at the end. All right, so what is a pressure regulator? A pressure regulator is a mechanical device that controls pressure and flow in order to self-adjust and control pressure on one side of the regulator. So I like to break regulators into two kind of primary categories, that being pressure reducing regulators and back pressure regulators. So if we look at this little schematic here, I think it does a nice job of kind of showing us what each of these types of regulators are doing. So if we think about having a pressure source, usually that's not at the pressure that we need to run our process. So we're going to reduce that pressure with a pressure reducing regulator, where that regulator is sensing the downstream pressure and controlling that downstream pressure. And that's going to our process. And then on the back end of that, we need another pressure regulator, a back pressure regulator, to control and sense the upstream pressure. So that way our process is always being maintained at the pressure that we want it to be at. So looking at a regulator itself, we can break it into a couple of different areas. So we've got the control element, which is controlling our flow and pressure. and that's going to be made up of our seat and our poppet. And then that's going to be tied to our load and sensing element, which is made up of our range spring. It could also be a dome load as like an external pressure force, where we, instead of a spring, we have a pressure source as that load force. And then our diaphragm, and this could also be a piston. And so those are sensing our pressure. In this case, our downstream pressure. So this regulator here that we're looking at is a pressure reducing regulator. It's sensing our outlet pressure. So we like to break down how a regulator works into a balance of forces equations. As an engineer, I like to think of it as a mathematical formula, and then it, all of a sudden it makes it a little bit easier to understand for myself. So looking at this cutaway here, we can see we've got our range spring force, our poppet spring force, our outlet pressure force, and then our inlet pressure force. And so if we look at it as an equation, our range spring force, F1, is equal to the sum of the other three forces. So our poppet spring force, our outlet pressure force, and our inlet pressure force. And we'll come back to this throughout the presentation and kind of look at each of these performance criteria and how how they relate back to this this equation that we've got. So let's jump into our first performance criteria, and that's going to be lockup. And so lockup is what happens when we shut off flow to our regulator. So downstream, we shut the flow off. And as we're shutting that flow off, there's a natural response for that pressure to build. And so as the pressure builds, the regulator tries to self-adjust, but because we're shutting that flow off, what happens is that with the balance of forces, we end up closing the seat of the regulator. And so then that small pressure increase actually gets trapped downstream of the regulator because there's nowhere now for that pressure to bleed off. And so we can see it in our flow curve here as we're moving on our flow curve. That first section there is what we would call lockup. And then, so as we turn on our pressure, we're going to see a slight drop. And then also as we go on the back end and turn our flow off, we're going to see that slight change in pressure there right as we close our flow. So on the opposite end of our flow curve is choked flow. And choked flow is essentially when we've maxed out the flow that can get through our regulator. And so if we look at the flow curve, we're all the way at the end there. And at this point, our regulator is going to act as a restricting orifice. So it will not be able to control pressure. The outlet pressure is what it is based on the orifice of the regulator. And then if you try to adjust it, it's not going to do anything. It's just going to maintain that outlet pressure, whatever it's at. And so we want to avoid being or operating within choked flow. So how do we address lockup and choked flow? So with lockup, what we want to do is understand how this slight increase in pressure when we close our flow may impact the rest of our system. So that means operating within the optimal flow range of our flow curve for that regulator. And we will get into flow curves and sizing and selecting a regulator in a future installment, so do stay tuned for that. Another option for addressing lockup is going to be using a softer seat material. This does come with its downfalls, but it is an option for looking at lockup. So for addressing
that, real quick, we had a quick question on with regard to lockup. Does this mean that we need to use a relief valve downstream of the regulator?
Yeah, great question. So hate to use the term always, but we pretty much always recommend using or installing a relief valve downstream of the regulator. And this is for a few different reasons, but it's certainly possible that that slight increase in pressure might be enough that there's something downstream that we want to protect from that. So you may want to go ahead and install the relief valve for that reason. There are some other reasons that we'll get into in the future around installing a relief valve downstream of a regulator, but it's pretty much always recommended to do so. Yeah, great question.
Perfect. Yeah, I just had another quick note. Unfortunately, people who are viewing on mobile devices are not able to ask questions, but we'll have our contact info later on in the slide deck. So please feel free to reach out and message us directly.
Perfect. Great point. So in order to address choked flow, this really gets into what regulator we are selecting. So before this regulator gets installed, we want to make sure that, okay, what's our flow rate range going to be? What's our maximum flow rate? And then that will allow us to select the appropriate regulator for the application to meet that flow requirement. If we have a regulator we're maxing out the flow capacity of that regulator, we need to consider bumping up to a larger size regulator. Adam, do we have any other questions after that?
We are good for now.
All right, perfect. So the next performance criteria we'll go over is Droop. And Droop is going to be the change in outlet pressure as our flow rate changes. So if we look at a traditional flow curve like pictured here, as we increase our flow rate, our outlet pressure is going to drop. And so what's happening here is as we increase our flow, our spring in our regulator is going to stretch. And when the spring stretches, the spring force is going to reduce. And so if we go back to that balance of forces equation, we've got our spring force reducing. So then looking at our equation, the only other force that can change is our outlet pressure force. So since our spring force and our outlet pressure force are on opposite sides of the equation, if the spring force goes down, our outlet pressure is going to decrease. So over time, as you increase that flow, that spring is going to stretch, which reduces the spring force, therefore reducing our outlet pressure. And so how do we address droop? If we have a regulator where our flow rate is very consistent and it's not going to change much, then we're pretty much at one point on our flow curve and our outlet pressure should stay fairly consistent with regards to droop. So we shouldn't be too concerned with droop if our flow rate is very consistent. Now, if we want the regulator to be able to handle a range of flow rates, that's where we need to consider droop and how to address that. So the first thing we can do is to just adjust the regulator, but this isn't always possible. So if we want to adjust the regulator, you could stand there next to the regulator. As you see the outlet pressure change, then you just adjust the regulator to get back to where you need to be at that flow rate that you're working with. But this isn't always possible if you've got a regulator out in a processing unit. You can't stand next to it and adjust it. Or if it's operating in a tool and a manufacturing facility, you want the regulator to do what it's designed to do without someone having to touch it. Because usually when people touch things, that's when things get messed up. So we want the equipment to work as it should and as it's designed to. So that's where we'll get into regulator selection. And I know this term's been thrown around a lot, but we're talking about regulators when I say this. We want to flatten the curve, and this is the flow curve specifically. So we want to have a very flat flow curve, which means if our flow rate changes, our outlet pressure stays the same. So some things that we can look at are a longer spring. And so if you've got a longer spring, there's a smaller spring rate. And so if your spring is moving the same distance, regardless of its length, then you're going to have a smaller force for a longer spring, which means less droop. The other option we can consider is having a dome-loaded regulator. And so this, for those of you watching the slides, we do have a dome-loaded regulator pictured here. And so what that is doing is applying a pressure to the dome of the regulator rather than a spring. And so since there's no spring, the spring's not stretching, and so you're therefore reducing the droop that you're going to see. We can also add in external feedback, which will tap into the downstream pressure and apply that to the dome of the regulator and act as a control loop mechanically to really maintain a stable outlet pressure over, we can do a pretty wide range of flow rates and keeping that outlet pressure very, very consistent. Adam, do we have any questions from the group?
Yeah, we got a couple of great questions. The first one would be, are there any regulators available that have integrated venting for relief?
Yeah, good. That's a really good question. So there are definitely regulators that have a venting option. So some will self-vent. So if you adjust the regulator to, let's say, decrease the outlet pressure, it can self-vent. If you're working with an inert gas, it could self-vent through the cap if it's, like I said, inert. If it's not, you can capture that vent and send it somewhere else. We do say that we should not use that as a relief device, but it's more so eliminating the need for a vent valve downstream. But again, so if we do have that venting option with the regulator, we want to also consider a relief valve in the system. But yeah, great question.
Perfect. And then we have one more. What sort of filtration would you recommend when installing a regulator?
Yeah, another really good question. So this is another scenario where I hate to use the term always, but for the most part, I'm always going to recommend using filtration with the regulator. There's soft sealing materials in the regulator, and they can be damaged. And I think lack of filtration is one of the #1 reasons that we see regulators coming back or not operating properly in the field. So we will get into what's called creep in a future installment of this session. And so stay tuned for that. We'll kind of talk more about how that dirt and debris in our regulator can impact the performance of it. So great question. What else do we have?
We are all good for right now.
Perfect. So the next performance criteria and the last performance criteria I want to cover today is what's called the supply pressure effect. And this is when, let's say, our inlet pressure drops, our outlet pressure is actually going to go up. And when our inlet pressure goes up, our outlet pressure is going to drop. So it's kind of goes against what you might think happen. If you have a regulator hooked up to a cylinder and you're depleting that cylinder over time as you're using it, your natural thinking says that your downstream pressure will also go down. It's actually the opposite. You're going to have, as you deplete that cylinder, you're going to see your outlet pressure across this single regulator go up. And so if we look at our balance of forces equation again, we can see that our spring force is not changing. Our poppet force is also not changing. We have a change in our inlet pressure, F4. And so since our inlet pressure and our outlet pressure are on the same side of the equation, they act inversely to one another. So if our inlet pressure changes, our outlet pressure is going to go the other direction. So like I said in the example, if our inlet pressure is going down, our outlet pressure is going to go up. So let's look at a quick example of this. So say we're working with a regulator that has a supply pressure effect of 1%, and typically supply pressure effects are documented or published in the manual or the catalog for a regulator. You can find that information so that way you can do some calculations for your system. If we're hooked up to a cylinder starting at 3600 psi, and we're going to deplete that cylinder 1000 psi down to 2600 psi. We take that change in pressure and we multiply that by our supply pressure effect. So for this regulator, it's 1%. So if we're dropping 1000 psi, 1% of that 1000 psi is 10 psi. So our outlet pressure is going to increase. Remember, we said it does the opposite. So our outlet pressure is going to increase 10 psi. So if we had our regulator set to 50 psi, now we've increased 10 psi to 60 psi. You can see that it's quite a big shift in outlet pressure, you know, especially thinking if you had the regulator set lower, that could certainly put you in the range of damaging equipment downstream, depending on if you have sensitive instruments or things like that. So we do want to consider this and see how we can address this supply pressure effect. So a few things that we can do to address this effect, and one is going to be adjusting the regulator as the inlet pressure changes. So if you're standing right next to the regulator, you're working next to it, and you see that outlet pressure, let's say going up, you can adjust the regulator and get it back to where you need it to be. And that's not always possible, like we were saying before. So you want to hopefully select the regulator that will be able to have limited supply pressure effect. And so first way we do that is by having two-stage regulation. And so this could be two regulators in series, or like the regulator pictured here, it's actually two regulators built into one body. So one stage of the regulator, which it has the anti-tamper nut on the bottom here, and then the knob on the top end is the second stage regulator. So that's where you get your adjustment. The other thing we can add in is having a balanced poppet. And so this just gets into the design of the regulator itself, and it's usually a feature that you can order for a certain regulator. So if we look at a quick example here, so let's say we now add another regulator to our first example there. We still have two regulators, each with a supply pressure effect of 1%. So we've got 3600 psi going into our first regulator, and we're going to drop that down to 500 psi. And then our second regulator is going to drop us down to 50 psi, like we had before. So this time we're going to drop 2000 psi, so let's drop even more than the first example. So if we go down 2000 psi, that gets us to 1600 psi. So 1% of that 2000 psi is 20 psi. So our next, so after that first stage, we're going to go from 500 up 20 psi. That gets us to 520. And then after the next stage, since we're now changing 20 psi for the inlet pressure of our second regulator, that 1% of 20 psi is only 0.2 psi. And so now, since our inlet pressure for our second stage went up, our outlet pressure is going to do the opposite. So it's going to go down that 0.2 psi. So we had a set pressure of 50 psi. We're now at 49.8 psi. You can see that it's pretty darn effective to take and add in another regulator to our system. And so if we think about just having the one regulator, we'd be swinging it by 20 psi. So rather than 50, we'd be at 70. But now we're holding pretty steady pressure by adding in that second regulator. So that's all of the material that I had for today. Again, want to thank everyone for joining us for this first installment. Do look out for our future future series that we will send out. So we'll send out invites for that. I will pass it back over to Adam to answer any questions that you guys might have.
Yeah, thanks, Matt. The only other question that came in was if we're able to provide a downloadable copy of this information.
Yeah, that's a great question. So we are planning to send a follow-up email to this presentation. So feel free to respond to that or reach out. Our contact information is here on the page. Feel free to shoot us an email and we'd be happy to reach out to you and get you this information.
Yeah, and then we had another quick question about, is there any difference between absolute regulators and gauge regulators?
Yeah, that's a great question. So there is a difference for how they operate. So that a gauge regulator is going to be sensitive to atmospheric pressure. So you will see some slight variability, and this really comes into play when you're dealing with very small pressure changes. And so an absolute regulator has the dome or that load element isolated. So it's usually there's either a vacuum pulled or it's pressurized to some extent. So that way the atmospheric pressure changes don't impact the set pressure of the regulator. Yeah, that's a really good question. You could spend a lot of time talking about the differences there, but good question.
Perfect. Yeah, so I think that concludes our training for today. I really want to thank everyone for joining, and please, reach out to us directly, provide any feedback that you may have, and we're looking forward to putting out more of these Tech Talks shortly. But just really want to say thanks, Matt, and thank you to everyone for joining.
Yeah, thank you, everyone. We'll talk soon.